But that was my honors notes?
It was an ice.
Okay. Well, I'm going to do it anyway. All right, so we have the ionization of water, where we have two water molecules that collide and make hydronium ion NOH minus. And when we write the equilibrium expression for this, we call it Kw. And this is a constant value under standard conditions, which is 25 degrees Celsius. Remember, we talked about standard conditions being different than standard temperature pressure. Standard conditions, 25 degrees Celsius instead of 0 degrees Celsius. And 1 atm, Kw equals 1 times 10 to the minus 14th. Okay, so what we know from our equilibrium knowledge is that if we make the equilibrium shift in a particular direction, some of the reactants or products will get used up. So for example, if we add H3O plus, what direction does the equilibrium shift? Towards the reactants, which means some of the OH minus gets used up, right? So we saw that here in this table, where you had lots of H3O plus, and that made it so, like when you added H3O plus, going from 1 times 10 to the minus 7th to 1 times 10 to the minus 5th, you decrease the amount of OH to accommodate that change, that shift. Okay, so what this means is that for pure water, you can calculate the concentration of H+. So what is the concentration of H+? The stoichiometry tells us that for every H+, there's going to be one OH minus, right? For every one of these, there's one of these. So if I say X amount is equal to H3O+, then that's also going to equal OH minus, because it's a 1-to-1 ratio. Therefore, Kw equals X squared. And what is the square root of 1 times 10 to the minus 14? Right. You guys remember what the fraction is when you're doing an exponent for square root? 1/2, that's right. So this is like 1 times 10 to the minus 14th times 1/2. So 14 times 1/2 is 7. So in water, the concentration of hydrogen ion is 1 times 10 to the minus 7th. And we talked about this a little bit before, about what pH is. What is pH equal? Not exactly. So when we're dealing with all of these acids and bases, where's my little table? We're trying to compare things. I mean, how easy was it for you to compare the strengths of acids using that table of Ka values? Moderately easy, except that I had to go around and say, oh look, 1 times 10 to the minus 5th is a little bit smaller than 1 times 10 to the minus 4th. It's a little tricky sometimes. Like which one's bigger, 4.5 times 10 to the minus 7th or 1 times 10 to the minus 7th? 4.5 times 10 to the minus 7th. But see, it's not immediate. It's not like everybody shouted out the answer. It takes a little bit of thought. So the point of that is that instead of looking at numbers in scientific notation, we use the log function to take them out of scientific notation but still be able to compare their magnitude much more easily. And the way that we do that is we use the log function. So, negative log function, right, so that we don't have to deal with negative numbers. So pH is equal to the negative log of H3O plus, or H plus. Remember, those are the same. So in pure water, what is the pH? 7. So for those of you that don't know what log is, it's a button on your calculator. But actually, it just takes the exponent here. It takes the exponent when this number is 1. If this number is not 1, then it's a bit harder to do in your head. You have to think about it a little bit more. Okay. Also know, what does the pH scale go to? What is the range? 0 to 14. Well, where does that 14 come from? Yeah, this right here. This is where the 14 comes from. This is our limit. This 1 times 10 to the minus 14th. What is, if this is pH, what do you think POH is? Oops. Okay, so what would the POH be of pure water? Right. Negative log of 1 times 10 to the minus 7, so that equals 7. So we have a pH of 7 and a POH of 7. So what can you tell me about pH plus POH? They're equal to 14. Okay, I could also have derived this by taking my KW expression. Do you remember properties of logs? Definitely, somebody says. Okay, when I'm multiplying two variables, taking the log of multiplication, how do I break that down? Adding. Right. Oh, I forgot to take the negative log of this. Okay, so this, we're going to give it a new name. We're going to call this the PKW. Hopefully it's a little intuitive about why we would do that. Not really a question. Hopefully it's obvious why we do it. Just like the pH, POH, PKW. Okay, so we're going to do the same thing with hydrogen ion concentration, or the same thing with Ka's that we do for hydrogen ion concentration to calculate things like pKa, pKb. But we'll do that next time. Okay, so if I have a strong acid, like HCl, HCl completely dissociates into H plus and Cl minus. So, if I have a 0.01 molar concentration of HCl, what is the concentration of H plus at equilibrium? 0.01. Because it completely reacts. Okay, so my pH is equal to the negative log of 0.01. What's the negative log of 0.01? It's just molarity. Yeah, that's what the concentration of H plus is, molarity. So you should get a pH of 2. Okay, if the pH is 2, what's the POH? Good, 14 minus 2 equals 12. Okay, if that's the POH, what is the hydrogen, or what is the hydroxide ion concentration? Go backwards. How do you go backwards? What's an inverse log? It's the exponent, right. So we're going to say 10 to the negative 12th molar is the concentration of OH minus. All right, let's do one with it's not so straightforward. Let's say our concentration of HCl is 0.0038 molar. What is the pH? What is the POH? What is the hydrogen ion or hydroxide ion concentration? So you're going to take the negative log of 0.0038. 2.4? Okay, and then POH? Alright, and then OH concentration. And you can't leave a decimal place in an exponent. You actually got to put the little caret, negative 11.58. So what did you get, sweetheart? Negative 12 molar. Okay. So I want you to practice a little bit. I gave you a worksheet last time that has a grid that you can work on, or the stoichiometry problems that you can work on.